Well, this is Professor Robert Solis. Welcome to this video lesson. We're going to continue talking about K-maps. And so what do we have to do? It says solve the following circuit equation by reducing the circuit using K-maps. All right, and we're going to reduce the circuit using Boolean algebra. And then we're going to draw the circuit, the reduced circuit that is. We're going to be drawing AND gates and NOR gates, so forth and so on. All right. So here is our equation here. It looks like A naught, B naught, C naught, D naught is ORed with A, B naught, C naught, D is ORed with A naught, B, C, D naught is ORed with A, B, C, D. So in order to draw the K-map, what you'll do is you'll just draw this type of graph where you're going to be having rows and also columns. Now in this case, since I have 4 variables, I'm going to have A and B over here. Notice how this starts off. So it's A, B, and then starting from the top, C, D. All right, so for every single row, we're going to start off with 0, 0, 0, 1, then go all the way to the bottom, 1, 0, and then 1, 1. For a 2 variable across these columns, you start off over here on the left-hand side. So 0, 0, 0, 1, go all the way to the end, 1, 0, come back 1, 1, 1. So that's how I remember it. When I write them down, just 0, 1, 2, 3. 0, 1, 2, 3. Okay, so that is how you start off with your Carnot map. You draw this vertical line over here so that you separate your A, B, and C and D. All right, so now what I'm going to do is I'm going to do some drawing here. Specifically, every time I see the knot, I'm going to treat that as a 0, so or false. So this is the knot of A, the knot of B, the knot of C, and the knot of D. So we're going to treat all those as zeros. Whenever I see something that's not knotted, we're going to treat that as true, or 1. And so this is going to be 0, 0, and then 1. And then finally over here, I shouldn't say finally, this is 0, this is 1, 1, and this is 0. Finally, none of these are knotted, so we're going to say 1, 1, 1, 1. Okay, now that I have these numbers, let's go ahead and fill in the squares here based on these values. So 0, 0, 0, 0. Okay, so 0, 0, 0, 0. Ah, that's the square right here, so I'm going to put a 1 right here. 1, 0, 0, 1. Okay, so 1, 0, and then 0, 1. So the intersection is right here. I'm going to put a 1 right here. How about this guy? 0, 1, 1, 0. Okay, so 0, 1, and 1, 0. This guy over here, so I'll put a 1 right here. Finally, 1, 1, 1, 1. Okay, so 1, 1 is going to intersect with this column right here, 1, 1. So there we go. Now that I've placed 1s in the Carnot map, my goal is to try to combine as many of these as I possibly can. And we start off with the maximal combination, and then we work our way down. Here's the problem. I can't combine any of these. You can't combine diagonals. The numbers have to be either above, below, to the left, or to the right. Like if there was one over here and there was one over here, well, I could combine this one and this one, but there's, and by the way, since there's a one over here, there was a one over here. I could draw a circle around here and a circle around here, or a half circle, and combine those. I can't do that either. So, gosh, I think the only thing I can do is just to combine these separately. So here's 1, 2, 3, 4. So in other words, everything has one circle around it. No minimalization is possible because I wasn't able to combine 2 or 4 or 8 of these. So bad luck. It looks like this is pretty much the reduced statement. I can't reduce it any further. Well, if that's the case, then I might as well skip this part where it says using Boolean algebra because there's no reduction possible anyway. So we'll just go straight to the next section, which says to go ahead and draw the circuit. So this first part looks like it's A, B, C, and D, and all of the values are knotted. So you have A, B, C, D as your input values, and notice how I have all of them going through an inverter so that I could get the A naught, B naught, C naught, D naught. All of these are being ANDed together. So what I'm going to do is I'm going to use an AND gate over here. That's going to be the input for the A naught, B naught. I'm going to use an AND gate over here. That's the input C naught, D naught is the input over here, that is going to result in A naught, B naught, A naught and B naught, I should say, C naught and D naught. And then these two are going to go into an AND gate, so I can AND this and this. So the result is A naught, B naught, C naught, D naught. That takes care of this term right here. Similarly, we need to take care of this guy over here. So it looks like just B naught and C naught, or B and C are knotted. So B and C are knotted, A and B are not. Similar deal, put these both through an AND gate, put these both through an AND gate, and so that's going to result in A, B naught, C naught, D, and so that's where I get this over here. How about this guy over here, A naught, B, C, D naught? Okay, so A naught, B, C, D naught. Put those through an AND gate, I get this. Put those through an AND gate, I get this. Put these two through an AND gate, and I get A naught, B, C, D naught. And then finally, for our last term, it's A, B, C, D, so we don't have any inverters here. A, B, C, D are going directly into this AND gate. C and D is going through this AND gate, and then these two are going through this AND gate, so I end up with A, B, C, D. Finally, it looks like it's going to be the OR of these four terms. So this has to go through an OR gate, so does this. So do these two, they go through an OR gate. And as you can see, based on the output, this ORed with this, and this is being ORed with this. Finally, I have one last OR gate where I put this through here, so that I get these four expressions, which is exactly what's over here on the top. So in this case, no minimalization was possible, and I was able to quickly determine that using the KMap, using the approach and the technique that I just shared with you. All right, so this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.